Welcome to the P1 Classical Mechanics lecture series. This lecture is called P109.2, right? So this is the second lecture of 109, and earlier we have looked at geosynchronous satellites. So geosynchronous, and then what? Then we did about before that we looked at the moon and the Earth, right? The orbit system and the time period of moon to rotate around the Earth based on Newton's laws and the rotational motion, circular motion. Now what I'm going to do is that I'm going to do three problems, right? So there will be three problems, and in that problem I'm going to make a bit of a small change in this thing, right? Moon and Earth, because it is not actually, it was 27.2 days, something like that. That's the exact revolution period of moon around the Earth, which was calculated in 109.1. Now it is not the actual case, because the let's let's do that. Okay, so that's the first problem. And the second thing I'm going to do is that I'm going to calculate the tension inside a string for two rotating masses, right? Two rotating masses, which is a first mass and the second mass, rotating in with some omega angular frequency, angular velocity omega, around a central point. And then thirdly, I'm going to calculate the exact, okay, the tension as a function of distance. Okay, what will be the tension at each point in the rotating body, for a circular rotating body? Okay, what will be the tension in that string? So this is actually designed to make sure that you guys get the gist of the basics, right? The problems will actually make you think and make you a better physicist than anywhere else, anything else. So I'm going to do these three things. So first of all, let's look at the moon and the earth situation. So if as you know that there is what there is moon, okay, there is this earth, and there is moon rotating. So last time we have looked at a circular orbit around this whole thing, and we got into the idea of calculating that based upon the gravitational pull and the angular radial component of the acceleration, right? We balanced that. Now I'm going to assume these as two independent bodies rotating around. Okay, these are not. So basically what I'm assuming now is that there is actually a rotation of earth around the moon as well. Okay, so the moon has some mass of the moon, and mass of the earth will induce a rotatory motion of itself, of the moon around the earth's surface as well, earth as well. So it's a compound body rotating around each other. Okay, so it's a compound effect of a body. So two bodies actually are rotating around, right? So in some orbit, so in some orbit, and it will have a trajectory which will be different, and some compound trajectory, two compound trajectories about a center. Okay, fixed center. Okay, so these about this center of mass. Okay, the center of mass, which is actually what we will discuss later in the course. So in the about a fixed point, these two bodies are rotating around each other. Okay, that's the actual case. So we are going to step up and do that as well. Okay, that because that's the right way. So let's assume that. So this is the mass of the, say, earth. Let's call this m2, and this is m1, and there is a fixed point around which these both things are rotating, right? So the let's call this distance vector r1. Okay, let's call this r1, and let's call the other distance r2. Okay, so two distances. Now if the force will be, the gravitational force will be f12, because of m1 uh, will be minus g, what, m1 m2 by the distance, the total distance, right? So the total distance between the two bodies. Okay, so that will be what, total distance will be, let's call this r1 plus r2, let's call this s. Okay, So r1 plus r2 is equal to s, so that will be a distance s, right, square. Okay, gmm by r square in the r1 direction, r1 cap direction, right? And for the second particle, so f uh, on the first particle m1 because of 2 will be equal to similarly minus g m1 m2, the same thing, 2 masses by s square in the r2 cap direction, the negative r2 cap direction, in the opposite direction, right? So that will be the case in this direction, and the first, for the first case it is in this direction. This minus sign indicates the direction. Okay, so just like that. Okay, we did that. Now what I'm going to do is that I'm going to take the first one, right? I'm going to take either one of them. If you want, you can take, and then equate. There will be these are rotating, right? So there is a radial acceleration to it. So let's do that. So for the either of this case, you get the magnitude of g m1 m2 by r square, or sorry, s square, right? So that's what we said. So s square must be equal to minus some m1 for the first body, for the first particle, m1 r1 omega square, which is the radial acceleration, which we have discussed so many times, okay, in the last lectures as well. So let's now simplify what the value of r1 is. This is the force, right? This is the radial acceleration, which is here, and this is m1. So mass times acceleration in the opposite direction, that's why there's a minus sign. So that will be equal to the force of gravitational force. And now you can simplify r1, so that will be g m1 and m1 cancels, so you get g m2 by omega square times s square, or simple as that. And similarly, if you do for r2 the same thing, you take the second case, these both components of the gravitational force is the same, only the acceleration component changes, right? So the acceleration force will change, right? Radial acceleration force. So similarly for r2 it will be the same thing, g m1 by omega square s square, just like that. Okay, you can do that. So now we found out r1 and r2, right? Now r1 and r2, so total distance s will be r1 plus r2, so that will be g. I'm going to take the g by omega square s square outside, and you get m1 plus m2. Okay, okay, I don't know. Okay. So you get m1 plus m2, right? Simple thing. So you get that g1 plus g2 will be m1 plus m2 by that thing. Okay, so that will be the total distance. Okay, now what will be omega then? So omega will be the s, and s square will become s cube. So you get the top, in the top you get square root of g m1 plus m2 divided by s cube. Okay, that will be omega, that is the angular frequency, angular velocity. So now angular velocity, so you can calculate the time period of this whole rotation, right? So time period will be 2 pi by omega, oh my god, yeah, 2 pi by omega. So that will be 2 pi times omega, which is square root of g, square root of by omega, right? So it will be reciprocal of that, so it will be s cube by g m1 plus m2. Okay, now let's substitute for the case of moon and the thing, right? So or now you can say t square is equal to, as in the later case, earlier case we have used the equation t square, right? So Kepler's law, we correlated with that, so that's why the t square can be written as 4 pi square times s cube by g times m1 plus m2. Okay, so just like that. And now you can substitute for the values very simply, right? Very simply you can substitute for this compound system, you can substitute for the values of mass of the earth, right? m1 can be mass of the earth and m2 can be mass of the moon, doesn't matter. So now you can substitute for the values, and you get t square must be equal to, or t square must be equal to some 4 pi square times the distance between the earth and the moon is 3.82 times 10 to the power 8 meter, the whole cube, right, divided by 6, the g is 6.67 times 10 to the power minus 11. Mass of the earth is 5 point what 0.98 times 10 to the power 22 plus mass of the moon is 7.36. These are uh, these are facts you can use, just numbers, right? Times 10 to the power 22, so that will be that. And if you simplify those, use a calculator and simplify those, you get time period of the rotation of earth around the moon or moon around the earth. The compound system will be 2.33 times 10 to the power 6 seconds, or it will be equivalent to 26.96 days. Okay, so that's another way of calculating the time period of earth, right? It was actually 27, now it's a compound system because we neglected the motion of earth, right? So motion of earth around the moon was neglected in the earlier case, and that's why we just took the in the earlier time we just took the rotatory motion of the moon around the sun, earth. And now we have looked at the compound system because of the both interaction, the gravitational pull of the earth on moon as well as the moon on earth. Now it's a compound system, and now the time period has decreased, right? Decreased, so it is much more faster now. Okay, so that is an intuitive way of understanding physics. Okay, I hope you guys got that. Okay, there is a lesson in that. So every system, every mass has to be assumed. If it is comparable, then it has to be assumed in terms of comparable rotation, two body systems. That is much more efficient, and that's the most precise way of looking at it. So from now onwards you have to look at problems just like that. And now I'm going to do what I'm going to do next is a system. You have a system and you have a mass just like that, m1, and there is another mass, okay, call it m2. Okay, two masses, and these are rotating around this fixed point with an omega angular velocity omega. Okay, just like that, an omega velocity, and this is some distance d, and the second one is some distance 2d. Okay, easy. Now I need to find out what the tension in this string, right, in this point of this string. Okay, what will be the tension here? Okay, let's call it t1 for mass 1, and in this place will be tension t2, right? So the tension in this string will be t2, and the tension in the first string will be t1. Now how can you calculate that? So you can take the first case. This is very simple, that's why this is the first case, m1 first mass, and there is t1 here and there is t2 here, right? So this tension is pulling the string straight, right? So that's what happening. Now let's write down the equations here. Now you can know that the force here is radially rotating force, so it's radial acceleration. So acceleration is equal to what? Distance r times omega square, right? So force is equal to ma, which is m times r times omega square. Simple. So for t1, for the t1 you can see, for the first mass you can see that the forces here is first force, which is t2. I'm going to call this positive and this is negative, this both sides. So t2 minus t1 will be equal to the force, the rotating acceleration force. So it's mr omega square. Simple. Okay, or the distance is actually d, right? So distance is d, so substitute that, so you get m d times omega square. Okay, you got that. Let's call this equation 1. And for the second mass, if you take the second mass, you have only one side there is tension, right? So the tension is in this opposite direction because the string is pulling this mass to the inside. Earlier case it was this was pushing, pushing the t1, right? T1 in this direction. Okay, now the string, that's the funniest thing about tension is in opposite direction wherever you are located in. Okay, if you're pulling a rope from one direction, the tension is in the other direction. So the tension here only is t2, only the t2 tension is existing here. So now you can say that for that case you can say t2 must be equal to some m2, which is the second mass. Here it was m1, right? It's the first mass. Okay, so m2, what times what distance is what 2d, right? It is 2d distance from the center, so it's 2d times m2 times 2d times omega square, the same angular velocity. So now what I can do is that I can now equate this, let's call this equation 2, and I can equate these both two equations, equation 1 and 2. So I can substitute the t2 value in the equation 1, so you get what you get, t2 which is m2 times 2d omega square minus t1 must be equal to m1d omega square. Okay, so now what you got is that you can find out t1, so t1 must be equal to, so there was a minus sign. Okay, there was a minus sign here, I guess. Yes, there is a minus sign because the we took the positive side in this direction, right? So the negative in this direction, so the acceleration, okay, acceleration is to the inside. Okay, acceleration is to the inside, so there is a minus sign. Okay, our distance is measured as negative. Okay, so here it was not needed because we took the direction of t2, which is in this direction. We took this direction positive and this direction negative, so we have two sides, that's why it cancels each other. If it was one single equation, you have to take this side as positive and this side as negative, so it was separate cases, that's why we took the separate directions for easiness, just for easiness. So there is a minus sign which I forgot, I'm sorry about that. So there is a minus sign here. So you now you get t1 must be equal to m2 plus m1, and I'm going to take that as common, times what, there is a 2 as well, right? So it's 2m2. Okay, 2m2 plus m1 times d omega square. Okay, so that will be the tension, that will be the total tension in t1, and t2 we have found out, t2 we have found out, t1 we have found out, just like that. So this is also very helpful, and I think this gives you a lot of insight. Now the third thing I'm going to do is that, third and final thing, just to make you a better physicist, the final thing is I'm going to calculate the tension. Okay, tension of a rotating body around a fixed mass, and there is a string here. Okay, string here, some mass, string here, and I'm going to break down this structure into some delta r. Okay, just like that, some smaller mass, and I need to find out at each point what will be the tension. The tension will be different, so we have seen that earlier. We have calculated tension of a rope, right? Earlier lecture 105, right? 107, 108, I guess. So we have calculated that earlier. So basically here we have to look at the tension, varying tension inside a string. So you can write down the straightforward, write down the force because of the radial acceleration. So it will be radial acceleration, it will be some uh, minus, you can take the sign positive as well if you want. I just took the direction to the left as negative and right as positive. Okay, so minus some mass times omega square times r. Okay, if there is no mass, if the mass was the mass of the string, so let that be the mass. Okay, so mass is the mass of the string, there is no mass, okay, attached to the string. Let's find out if for the string itself what is the tension. That problem will be much more easier. So now I can break down the rope into smaller segments, and I can find out for some point this will be the tension T of r, and at some delta r, which will be T of r plus delta r. Okay, the new tension, okay, to tension will change just like that. Okay, so for some small difference of length delta r. Okay, so now you can write down some, so T of r at the end point, T of r plus delta r minus T of r will be equal to the gravitational, sorry, angular velocity force, right? Angular acceleration force. So it will be minus okay, minus times mass times delta r, which is the distance, minus times r times r, right? R, which is the distance, the total distance for the whole thing, times omega square. Now the mass of this small segment, right? So if you have a, earlier we have did the same thing. So if you have a whole thing which is a what 10 kilograms, and it has 2 meter length, right? Assuming that, then the 1 meter length will have 10 by 2 times 1, which is 5 kilograms, right? So basically using the same principle, the 1 meter length, half of that will have 5 kilograms. So similarly using that length, if the mass of the whole thing is m, right, the mass of the whole thing is m, then let's call this m by the total distance is l, right? Let's assume that the total distance of the string is l. So then mass of the string by l times some delta r, some small distance delta r, will be equal to the total mass. So total mass times r, which is here, right here, times omega square, will be the tensional change. So you can maybe write down T of r plus delta r as some T of r, which is the tension at r, plus some delta T, right, change in T, minus del T of r, right, T of r must be equal to m by minus sine l delta r times r omega square, just like that. Okay, so you have found out that, so T of r and T of r will cancel, and you get the rest of these things. So you get delta T must be equal to minus m by l delta r times r omega square, right? So just like that. Now what I can do is that I can integrate for the whole thing. Okay, I can integrate for the whole string. Now we have a small fraction of this string with a small fraction delta r with the tension delta T. Okay, now we can integrate for the whole string, and you get the whole tension equation, just like that. So let's do that. So integrate for some T of r to T of the whole string which has a length L, right? Yeah, T of r, T of L delta T must be equal to minus m by L, which are constants, and also omega square is a constant, take outside, and you get integrals from r to L, right? R to L r dr, just like that. Okay, now let's do the integration. So you get T of L, these are dt's and drs, right? So this is also dt for smaller delta t values. The r tends to small and small values. We have done this several times anyways, so we are limiting it. So tl minus t of r must be equal to minus m by l, m by uh, l, anyways you get the when you integrate r, you get r square by 2, so you get a 2 here, just writing that, times omega square, and inside you get l square within the limit, so it's l square minus r square. Okay, okay, just like that, I just did it. So now t of l will be 0. Okay, why is t of l will be 0? So if you have a rope like this, right, the tension will be the maximum at the point of rotations, right? The whole mass is on to the right side, right? So the tension will be the maximum here, and it will be the minimum here at the end, because there is no mass attached to it. So the tension will be the minimum at the end. So at the end, which is the length L, the tension will be 0, just like that. Okay, so I hope you understood that. We have did this earlier as well. We have derived the equation for tension for a rope. Okay, remember that we have did that. So in that rope itself, if r is equal to l, then it will be 0. Okay, if you just look at this equation, what happens if r is equal to l? So r is equal to l means this whole thing will be 0, so the tension difference will be 0, just like that. Okay, so now substitute that in this, substitute that, so tl will be equal to 0. You get minus t of r must be equal to minus m omega square by 2l times L square minus R square. So that will be the tension, and minus will cancel. So this will be the tension inside the string, right? The inside the string, the tension is going to decrease. Just look at this equation. It's going to be the maximum at this point at L is equal to R. Sorry. Oh, sorry. We just assumed that, okay, our
Okay, our integration was reversed, I'm sorry. So you have to go from left to right. Okay, so you have to go from left to left L to R, because we are integrating from minimum to maximum, right? So it will be increasing in the other direction. Okay, so just like that. Okay, it will be right, this equation is right anyways. So this will be the tension inside the string. Okay, just like that. I hope you guys got it. You can do it yourself. This I just did it myself right now. And this will be the way that tension will happen, right? So okay, this is actually, yeah, this is actually perfect, right? Because why is it perfect? Because if you go from small values to the maximum at the end points, okay, this is, I just thought wrong. Okay, anyways, if you get to the end points, the L, right, to the maximum, the tension will be 0. Okay, and if you are in the middle, in the center of the rotation, the tension will be the maximum. Look at this equation, it's a beautiful equation, just like that, right? You can never get anything better than this. So this is how the tension varies in a rope or a string or anything which has some mass. If mass is almost 0, then this tension difference will be very insignificant, so you don't have to worry about that. So here it will be valid and it will be beautiful. Look, this is a beautiful equation anyways. So keep watching lectures and give me the feedback, support me, subscribe the channel, please guys.